I'm Professor John Rarity from the University of Bristol, and I work on quantum technologies in general, but I've focused in my career on quantum communications, quantum sensing and quantum range finding, and a little bit of quantum computation. Quantum encrypted is probably a misnomer. What we are doing is we are creating secrets that are shared between two people at two remote locations, and those secrets cannot be shared, cannot be listened in on by an eavesdropper, by somebody who wants to sort of know what that secret is. And then that secret can be used, say, as a key to lock a box containing the messages that you want to send, the classical messages. And so that's the principle. In practice, what we're doing is we're using single photons of light to send encoded messages that, if they are listened to, are disrupted. So the message contains an error, and the number of errors we measure tell us how much the message has been listened into. And we use quantum principles of superposition and no cloning so we're using those principles to guarantee the security of this key sharing process. Once you have shared a secret key, you can use it for anything. You can use it to protect your PIN at the bank, or to protect your medical records, or whatever. Yeah. If you have two objects at two locations that have been transported there, like photons can be particles of light, can be transported to two locations quite far apart instantaneously, virtually. And when you measure them, you might expect them to show some classical correlations. And those classical correlations mean that you will only achieve a correlation level up to some point. If they're quantum correlated, the two photons, or entangled, then those correlations are 100%, no matter how you measure them, as long as you measure them equally in the same way either end. And that 100% correlation is a signature of entanglement. If somebody is listening in, or somebody is disrupting your channels, then the 100% correlation is lost, because you're moving to a classical communication. It's eavesdroppable. So measuring the fact that things are entangled and properly highly correlated means that you have the guaranteed security, because you know you've not been eavesdropped in an entangled quantum key distribution system. Free space quantum key distribution is very easy and quick to set up, but is very susceptible to being spoilt by atmospheric conditions. So if I want to send a laser beam over 10 kilometers, by the time it ends up at the other end, it is wandering about because of turbulence in the air. So free space quantum communications on the ground is limited to 100, 200, maybe 300 meters for reliability. We have done 10 kilometers and 100 kilometers, but up mountains where the air is thin and turbulence is less. Then points to where free space communications will be, of course, always has an advantage over fiber optics, and that's in space, because there are no fibers in space. So fiber optic communications is only useful where fibers are installed in the ground, and then that's what you would do. QKD over long distances on the ground, you do it in a fiber, and you can very easily sort of find that, yes. So that works well. But in space, you have to use free space communication. So much of the work we have done on free space optical key distribution, quantum key distribution, is really aimed at proving the principle that it could be done in space. The QKD experiments that we focus, so the technological challenges were overcome because we had already developed detectors that could count single photons. And having a detector that can count single photons and is efficient meant that we could do single photon interference experiments and thus demonstrate the feasibility of QKD in fibers. When we moved to free space, we were trying to do the same sort of thing in free space with polarization encoding, polarizing the photons and using that to encode the information. The challenge there was very quickly the problem of maintaining beam stability in real atmospheric conditions. So if you go over a kilometer, one of our early experiments was over a kilometer above a runway in a disused airfield. The runway warmed up, the air wandered about, the beam went everywhere. At the end of the day, it began to get misty and it began to get very stable, and you got stable conditions. We got key distribution for an hour, and then it went bad again. So that was the problem. You had to wait. That was the challenge. You had to wait until things calmed down and catch it. And also, you had to make sure that your QKD, your quantum key distribution system, was working perfectly before you took it up the mountain. And we worked that out when we got up the mountain, and we spent most of our time trying to get the QKD system to work when it would have been much easier to get it working in the lab rather than up the top of a mountain where one part of the QKD system is on one mountaintop and the other bit is over there on the other mountaintop. So preparation was the challenge. We switched to free space because we were working in a military organization and because we had, in some ways, given the technology to our telecoms industry in the form of the British Telecom Company. They took on the fiber optic quantum key distribution, and they were much better with the fibers. We gave them the photon counting technology, and they went off and then covered the fibers in the UK. And and the military said, well, we probably need battlefield or key exchange to vehicles or whatever. So we decided to do free space there. Then towards the end of the 90s, we realized it was difficult in atmospheric conditions to get reliable quantum key distribution. And we began thinking about doing key distribution up to space where maybe the air is a little bit clearer. So that's when 1998, 99, we began thinking about key distribution to space. And then we got funded to do a feasibility study in 2000 by ESA, by European Space Agency. And so we did some of the first studies of whether it was going to be possible, whether the loss was too great, all of those things. I think Europe's challenges are that they tend to be sort of distributed, and various groups are competing to do the same thing, which reduces Europe's competitive abilities with respect to countries where maybe the funding is focused into sort of the strongest groups. So, for instance, the Messias satellite is a very clear example that if you focus your funding, you can make much quicker progress. On the other hand, some of the best groups in the world are in Europe in quantum information. At this conference, we've heard talks by excellent groups from Europe for smaller projects. With the funding schemes like the European Research Council, people can get very focused funding for long periods of time and become world leaders. Particularly in Germany, they have a 10-year funding cycle. It means that you can start an experiment and you don't have to, you can make it so complicated in 10 years that you will definitely be world leading. So I think there are good aspects and bad aspects to the European funding schemes. It's a shame that the UK left Europe and left some of those schemes, but we've rejoined ERC, we've rejoined some of those joint projects, which we found very good in the past when we were members of the European Union. I mean, you can hear I'm very pro rejoining the European Union. But yeah, so in respect to China, China's now, what I see at this conference again is that many of the best students that Europe recruited from China have come back due to the initiatives that the Chinese government has to recruit the best back here to set up groups in China. And I see more and more, particularly in the field of quantum information with the Zhang Wei-Pan group, that they are competing on a level or even above as they're beginning to overtake their European counterparts. Where China has focused the funding, they've been able to really compete and overtake the UK and European and US groups. On human society, I think there will be new ways of measuring environmental pollution. We're working on things like that in Bristol. But in terms of sort of, there is an artificial intelligence revolution happening now as we speak. And the question is, how is that revolution going to interact with the quantum technologies? Will there be quantum AI? Will there be computers, quantum-based computers that use AI-type principles to learn and make decisions with the added power of quantum information? I'm not sure. First, I would hope that in the next 20 years, we actually have a working quantum computer technology that can do some of the simple tasks that are driving the field, such as factorization, such as simulation of molecular structures and things like that, which we know of at the moment, but which we cannot yet address significant problems such as the design of drugs. But that's where a significant impact would also occur, is if the quantum computer becomes ubiquitous, in other words, that easy to build. We see it as a big challenge at the moment, but once they're built, could we use them to design drugs, molecules that do specific tasks, solar PV collection, all of the things that are done by conventional computers, but with approximate methods, could we do them more accurately? I wait to see. Once I've got a quantum computer, I'll start programming it.